and we also have to choose where the brace goes anyway. This forces our hand. We consider that a win, and GoFump can fix it anyway. The next token is actually inside the body of the function now, which is the Fump identifier, which of course came via the Fump import. It is not a coincidence that it's the same word, but of course it didn't have to be. It could have been a different name. And this brings up the point about readability that I think is important to the way Go works. And again, sort of flowed out of the design process. Every identifier in a Go program is either local to the package or it's a qualified identifier with a dot in the middle. And that is a profound effect on readability. You don't get this idea that when you do an import, the identifiers come into your namespace. What happens is one identifier comes into your namespace, which is the package name. And all of the package name component, all the package's components are bound to the package name as kind of a little namespace, or if you like, sort of pseudo structure. That means that you never have to look very far to figure out what an identifier is inside a Go program, and that's a really important aid to readability. I also should probably point out that this word is fumped, not format. That's my fault. I will tell you right now, it never occurred to me to make it format because I knew that you were going to type this word, however it was spelled, in probably the majority of all Go programs ever written because it was the formatted print generator. And by the second or third time you typed it, you knew what it meant. It did not have to be the full format word. There are people who disagree with that. I respect their opinion, and I move on. Okay. The next token is a period. There's actually a lot of uses for the period token in Go. It means a lot of different things. It could be accessing an element of a package, an element of a structure, a method call, a function call. Early on, I remember Ken complaining that we had too many uses of dot, and he wanted syntactically to have a different character there to split the uses out for something. It might have been method call. We pushed back and convinced him it was okay, and he acquiesced. But it does mean that when you see just A.B in a Go program, you don't actually know what it means unless you look up A and understand the type. And you can parse Go without a type system, but you can't analyze it semantically without the type system. That's fine. But it does mean that you have to understand what the types are of an expression to know what it means. I don't consider that a problem, particularly because in practice, humans seem to have no trouble with this. When they see the dot, they know what kind of a dot it is. It doesn't bother them. One thing that does come up here, though, is that there's no, what would in C be called the arrow operator, the points to operator, because if the thing on the left side of the dot is, say, a structure pointer, and the right-hand side is a field tag, field name, you don't want to have to type *thing.field. So we automatically insert indirection operators for you in order to avoid having that operator. That adds yet another meaning of dot, but one that we're quite happy with. I think the programs just look nicer as a result. Println. Notice it's capital P instead of lowercase p. That's because capitals are there for export. You all know that. I don't need to beat that up. I'd like to talk for a minute about the design of this thing, though, because it's actually a little bit of a story. We always knew that formatted printing was going to be reflection-driven. It wasn't going to be like in C where you have to explain the arguments, because that's not type safe. You have to actually understand the dynamic type of the object you're printing in order to safely be able to print it. Also, maybe even more important, because you know the type of the thing when you're printing it because of access through reflection, you also don't need a format. And so you can actually have a println in Go, which you can't have in a more weakly typed language. And so we knew that reflection would get us there, so println made it possible. And I think, in fact, most of the time people don't use format strings unless they're like formatting fancy error messages or something. Print or println does the work for you. And that's a consequence of knowing from the beginning, even before we understood how reflection was going to work, which was itself a very long story. We knew that that's how it was going to work, and so we designed for it. Println and his friends, they're all variadic functions. Go is very strong in variadic functions. The original form of a variadic function just had ... there, which actually came right out of C. There was no type on the ... It was always empty interface implicitly. And then one day Russ said, why don't we just make a type there? And so we didn't quite know what to do with that yet. Of course, it turned out to be a really great idea. It took us a while to get there. But on February 1st, 2010, the empty interface went onto the ... And so the signature of println became properly defined then. And the idea of the relationship between dot, dot, dot and slices became general and actually quite powerful and very easy to use. Open parent, not much to say. Traditional function syntax, no messages, no function application with space. It's just old school open parent. Then we have a string. Now, I picked a string here with some Unicode characters in it. That says Nihongo, Japanese language. Pardon my pronunciation, Japanese gophers. One of the most important things about Go that was settled very early is that the input source is defined to be UTF-8. Now, since Ken designed UTF-8 and I helped roll it out with him, you knew there was going to be a UTF-8 language, going to be very strong. But I think it's really important to point out that we just declared up front Go is a UTF-8 language, period. There's no encoding question. You're not allowed to write it in some other language, because that means one thing happens beautifully smoothly, that if you don't define that, it doesn't work very well at all. And that is this string here, this thing with the Nihongo in it, you know the representation of those characters in the source code is UTF-8. And so it is well defined what non-ASCII characters look like in the source code. It just falls out automatically that the representation of strings outside the ASCII plane is UTF-8 characters in the source code. It's kind of a magic trick. There's nothing there, and yet it just works. And it's hard to explain in a way that makes it sound interesting, but it's true. And I think it's really important to understand that. And no other language that I know of actually does this. I'm sure there are some, but all the predecessors that I know of certainly did not define this way, and so they struggle with the meaning of a large character value. And then, of course, there's a whole question of what a string is, and it turns out it's an array of bytes with a couple of special properties. The string literals are the most important part of it. It was actually one of the very first things we wrote in the Go spec. It was written in probably that first week, and it's hardly changed at all since then. Every detail of that was understood very well up front because, of course, we'd played in this space for quite a while. And if you want to know more about it, a few months ago I wrote a detailed blog post, which is probably a better place to read about it than have me blather on. Then you get to the closing parent of the function call. Of course, there's no semicolon there. The semicolons went away shortly after the release. I just made a wonderful change to the language. I loved it when it happened. But I should point out that before then, semicolons were optional in a very confusing, hard to understand, constantly changing way. We struggled with the grammar. I think at one point there were more productions in the Yak grammar to deal with optional semicolons than with the language proper. It was really difficult to sort that out. And one day we just said, I think Ken actually came in and said, why don't we just fix this? So we went back to Martin Richards' idea from BCPL, got rid of semicolons by injecting them in the lexer. And it changed the language a little bit because you had to format differently, but I think it was a huge win. And closing brace. And there we are. That's the end of Hello World. There's a whole bunch of things I didn't talk about in this program. I didn't talk about the types very much, what constants are, they're kind of magic in Go, methods, interfaces, how libraries work, how memory management is. It was garbage collected from day one. We never considered any other option. Concurrency, of course, which is coming up. And then there's the various tools, the ecosystem, the community, the outside world, the ecosystem that develops around that. And I want to point out that although I've talked entirely about the language so far, the language is central to this story, but it's really only a small part of it. It's the entire thing that builds around the language that makes success happen. And the factors that bring that success in are, I think, building on the history, understanding through a lot of other languages and years of working in software development, what matters in a language, what doesn't matter in a language, the experience that comes from working for a long time, the process of design. Almost all of Go was defined in the first year and a half or so by Ken and Robert and myself, huddling down, arguing, debating, disagreeing a lot. Nothing went in until all three of us agreed that it was a good idea. And that's because we all came from very different backgrounds. And so it was important to understand that if the three of us agreed, it was probably a rock-solid idea. I think it's a really important part of the Go story. And later, of course, Russ and Ian and others came in and helped us make it much, much better. But I think this idea that you have a small team designing it and not just sort of taking a suggestion box and making things happen is a huge part of why Go works the way it does. But once we'd sort of got to where we thought it was right, we stopped. We said, this is it, this is the language. Go version 1 comes out and locked it all down. And that's a huge part of the story. I'll come back to that point. Now I want to go through a second program. That was Hello World. Now we need to talk about concurrency. And I think a good way to do that is to somewhat more quickly go through the first concurrent program that I ever saw, period. And that was first one written in Go. It came out of a paper written by Tony Hoare in 1978 called Communicating Sequential Processes. And the problem is, of course, the prime sieve. What we want to do is to print in ascending order all primes less than 10,000. It uses an array of processes called Sieve, and each process generates a prime, passes it down to the next one, and there's a chain that develops of filter processes that filter out the details. I suddenly lost, oh, there you go. In 1978, this paper appeared. It actually showed this whole thing. Hoare credits David Greaves with this beautiful solution. I should mention in passing, this is not the Sieve Veritasities. It's not very efficient, but it is kind of beautiful. Look at it. This is the original one. This is the complete presentation of the program in the CSP paper. There's no description of how it works. You have to puzzle it out. And I won't go through it all. I'll just point out two important points. Everything is in here. There's actually sort of a vague select statement down the left column. The star is a loop over all of the Sieve processes. There's an array of processes, which is instead an interesting idea. And it's fundamentally the same program that you probably know, but it's just structured a little differently on the page. The other important point is that there are no channels in this. It's a rigid structure. There's just a fixed set of 100 Sieve processes. 100 is known to be enough because it's the square root of 10,000. It's a theory paper. He's proving a point. That's fine. But because the original CSP had no channels, this is the best you could do. It's still an interesting program, but it's not very flexible. So about 10 years later, I had been futzing around with some of these ideas for a while and decided I wanted to play with them for real. And so I wrote a little toy language called Squeak. And Tom Cargill wrote the prime sieve in Squeak first. I think he credited Doug McElroy through it, but it's a longer story than that. This one, however, uses channels. Squeak had channels in it. And so the length of the run of primes is entirely programmable. The program is much more flexible. For modernized, it's a little easier to read, I think, even though it's a weird little language. I will point out that I don't actually know where the idea of channels came from. I don't claim I invented it. I really don't think I did. But I don't know where I got it from. It was floating around somewhere. And the later CSP book has channels in it, but the original paper does not. But anyway, Squeak had channels. You can probably read this program and pretty much understand what it does. It's it's atom breading a lot of Go's properties. You can see a couple of key points here. The left pointing arrow operator for communication. And the next slide, you can see the colon equal guy squeaking in. And keen eyes will also notice a mook, which became make in Go, but that's just a coincidence, sort of. This program runs, by the way. Yeah, it's a very long line going off to the right. We should fix that, Andrew, wherever you are. But it prints them all. Jumping ahead, 2008, March 5th, we actually started writing the spec in Sydney on March 3rd, 2008. 2 days later, Robert said, let's write a program. And so into the spec, we typed this version of sieve.go, which I think is correct, but it's very different from the language today. You can notice that those are pointers, an issue that we struggled with for a long time. They're pointers to a built-in structure that gets built. They still are. They just don't look like that anymore. The operators for send and receive came from the shell, greater than and less than. And you can recognize the program, but it's a little different. And it, of course, you'll notice, one other thing, you'll notice that main is uppercase. That was the early days. It might have been my fault. I think I was typing. But you can recognize, you can actually understand this program in modern Go terms and translate it pretty easily. But it mutated quickly. In July, we decided that greater than and less than didn't work because it was confusing to have unary operators when there were already binary ones with a completely different meaning. So we changed them to be these weird little funny sort of pseudo arrows. That helped a little bit. Channels were still the pointers, but at least we got rid of the capital on main. And so it's a little closer to current Go, but it's still kind of weird. And then about a month after that, there was a discussion where Squeak's operator came in. It got a lot nicer. We now had prefix arrow for receive, infix for send. Channels are still pointers, though, and so there's still some confusion about how you make a channel and what it does. But you can still see the change happening. Notice that, for instance, chan, it's a new chan int here rather than a make, because on early January 2009, we finally figured this out. We split new into new and make. The things that were pointers to built-in structures were called make, and so channels were made rather than nude. And that, some people still struggle with that concept. I don't think it's hard, but it is clunky, I admit, but it does the job. The code, however, is wrong in this example. This is out of the spec on that day because there's still a star left, and the channel types on the filter function are completely garbage. We didn't run it because, again, we were idiots. So this doesn't work. But then just before the release, I finally said, we should probably make sure the Sieve program actually runs in the spec. And so I went through, and sure enough, it was broken. So the capitalization now is gone. I brought in Fump. This guy actually runs. And this is modern Go except for the semicolons, which went away on December 10th, 2009 in the great semicolon purge. So this is the program that, you can recognize it all the way back to new Squeak, really. But it mutated very slightly, but converged fairly quickly. The piece that's important here is that the historical refinement of through languages, through thinking about the ideas that are there, is again, this process of history and decision process and time to get us to here. So this beautiful solution was contributed by a decades-long process of design. One thing I did not discuss that's extremely important to Go is select. A lot of people read about Go or knew about concurrency from other languages and will play in their language of choice and implement channels and coroutines and say, look, it's Go-like. It's not. If you don't have select, you don't have concurrency. You don't have real concurrency because it's a connector for channels. Without select, all you can build is linear structures. You can't build the interesting trees and loops and other complex structures, which are the key to building true systems that use concurrency well. And also, I'd like to point out that select is the only part that's really hard. Everything else is easy. Channels are just queues. What's the big deal? Select, though, that's tricky to get right. It's also tricky to design right. And Go's select, again, is the process of refinement through a series of predecessor languages originating with CSP to get the semantics right. And in Go, we spec'd it out on March 26, 2008. And at that point, we knew some of the things that needed to be fixed for the select in Go included making sure it could be implemented efficiently, making sure it's scaled right, getting rid of some of the features of select from other languages that were nice to use but made things too complicated or too hard to make highly efficient. But that aside, the Sieve program that I just showed you from 2009 is exactly the same as the one in the spec today. So that's almost 5 years with no changes whatsoever. And open source systems are usually not that stable, right? They get tweaked and work, certainly ones that are used. They're always being adapted, changing. And that's a good thing because you can make them better. But I think it's important to recognize that one of Go's key elements of success was stopping the change at some point. And we just said, Go's done well enough now. It's not perfect, still got a lot of problems. We know we screwed up a bunch of things. But it's better to just say we're done than to say we'll fix that and keep breaking people's programs. It's a really important reason for Go's success. So this is the trends graph from trends.go.com for the keyword Golang. Down the bottom, those two dates are 2011 and 2013. Go 1.0 came out in mid-2012. And I think you can see there's a distinct bend in the curve. It got suddenly much steeper when Go 1 came out. And I think that's evidence that people really need that stability in order to trust that they can use this system and make something out of it. It's a really important point. And so looking back, what are the factors for Go's success? I'm obviously biased. I was in the middle. I don't know why you guys like it. I know why I like it. But I can take a guess at what matters. The features and tools are obviously important. Everybody talks about how great Go Fump is and things like that. The concurrency is a huge draw. Having a nice statically typed language where nice and statically typed don't often go together is nice. The concurrency is a huge win. People love that. It's also, I think, one of the draws that brings people in for the first time. Having a strictly garbage collected language has its issues, there's no question about it, but it makes the language very attractive to start in. The compiler being fast, the binaries running quickly, this notion of static type and dynamic field that we tried to get right. Having a really good standard library, but limiting what it is so that it's outsiders can bring in more stuff. We don't have to put everything in the core. Works really well. The tools are critical to what happens. The Go command, Go fix, Go Fump, things like that. But also the factors which were part of the design process all along to make sure those tools could be built. that the grammar is easy to parse, fast to compile, that the language doesn't have fancy semantics, that it's easy to read, easy to understand, easy to translate. Those are all important factors too. I mentioned Fump many times. This other concept, which I talked about in a splash talk a year or so ago, that Go was always designed for Google internally, and we're a big company with a lot of programmers, and we want to make sure that the language works for large teams working on large programs. That's sort of an intangible thing, but I think Go has a lot of features or lack thereof or design elements to make sure that programming large really works. So less obvious than those things I just listed is sort of the process by which Go came to be. We started with the idea that we needed a language to make it easier for us to get our jobs done. And our job is writing server software. And so we stayed focused on that idea. We're trying to solve the problem of writing server software. There's this process we went through of concentrated development, really intense for several years, followed by a freeze. We planned for the freeze, we worked hard to get there, but then we stopped. The language is done. And so that was a huge, this concentrated effort, understanding, really being involved, but then knowing when to stop is important. This idea that it was the consensus-driven design by a very small team is not unusual exactly, but it's not how everything gets built. And it really is important to the clarity of the vision of the language. But then, of course, it went open source. We got incredibly important contributions from a community that I'm happy to say seems to get what this is all about and appreciate what it's for. Go wouldn't be anywhere if it wasn't for you guys. And so the consequence of all this is we developed this really rich ecosystem of externally provided libraries and tools. The port to Windows was done entirely in the open source world. That's fantastic. That's a consequence of all of these other things tying together. So in other words, Go succeeds because there's an open source community that understands our mission and helps us achieve what we want to do, which is to build something good for today's world. So that brings me to my final point here, which is what I call fitness to purpose. In March, a month ago, this guy, Donnie Burkholz, maybe he's here, I don't know, wrote this article on RedMonk entitled Go, the Emerging Language of Cloud Infrastructure. Now, the emerging part is cool, I love that. But if you drop that, it would say Go, the language of cloud infrastructure. That doesn't really surprise me because Go was designed to be a language for cloud infrastructure. That's why we did it. That was the whole point. We used to call those things servers, now it's called cloud infrastructure. It'll be called something else next year. But that's what we did. And I think he wrote a really nice article about why Go is succeeding and defining that it is succeeding. He's got this lovely little graph here. And again, it shows that sort of distinct kink in the curve and very steep lines to the right, which I think is very encouraging. And so that brings us to the next phase, which is the future. And that's where you guys come in. So we're passing the torch off to the open source community. Make something exciting happen. Thank you very much. Q&A? We have questions? Time for questions, okay.